Hi, so this is an introduction to validation V model. This is a standard used by the pharmaceutical industry, but it can be applied to any project. So if we imagine that we have a project to design a piece of equipment, it has a life cycle for the project. So there's a time from the project being started to the time it's finished. At the beginning of the project, we identify the need, why we need this piece of equipment. We then design and we build, and then we qualify. Now, excuse my handwriting. So, the need defines what the project is going to be about. The build is where we actually spend some money and some effort and build the thing. And qualify is a pharmaceutical term for commissioning. The trick of the V model is the way it self-tests itself. So once we've identified need, we put together a group of users, and the users define a user requirement specification, a list of quantifiable factors to do the design. These are all SMART in the sense that they are specific, measurable, achievable, realistic, and potentially time bound to the project. So URSs don't include things like specific solutions, they only include specific questions, but they also they have to be things that can be quantified to a numerical or a yes/no result. Then once we've agreed that the URS is complete, and there'd be a committee here that would be constantly feeding back on itself over and over again, checking that the user requirement does meet all the requirements. So this is things like it must be compatible with our power supply, it has to produce a rate of so many units per minute, the emissions have to comply with a certain standard, that sort of thing. We then pass the URS on to a design team, and this may be within the company or it may be within a series of contractors that we ask for quotes from, and they design a functional requirement specification. So this is URS is what it does. I just change colours here to say what it is. URS, what it does. Functional spec is how it does it. And then the next one, so functional spec is it's going to have start-stop buttons, it's going to use a particular mechanism, it's going to have a conveyor belt, it's going to apply a certain physical quality. Again, with a functional spec, as whoever's designing the equipment, as they come up with questions about whether they can or can't meet user requirements, or whether there's more than one way of doing something, or if a certain thing is a problem, they go back to that URS committee and it goes round again. Then the designer will come up with a design specification. So the design specification, in terms of what we're doing here, is it's the detail of operation. So in the function spec we say it has to have a stop button. In the design specification we say the stop button is mounted on the front panel. The stop button is red. It's a PDL type 51 stop button with a key. It's a very specific construction. In terms, I don't know if you've ever come across it this way, but function specification is the characteristics of the machine, the way it behaves, and design specification is the features of the machine, it's the things it physically has mounted on it. And again, there is this whole thing about, sorry, just ignore this. There's this whole thing about feeding back. So the designer will internally check his design, he'll compare his design with the functional specification, and he'll bounce any queries back to the user requirement spec. anything that goes back to the URS, you'll notice these arrows go one way. If the designer has a problem that requires the URS to be changed, once the URS is changed, we go back to the functional spec. We make sure at every stage that this is what we want. So that when we come to the build, we have a design that on paper is perfect. The problem is it might not be. So then we want to test that the design is what we built. This is testing that physically what's been delivered to our site, installed on our site, is actually what's been designed. So we call that an installation qualification. Okay, so this is what's installed. The machine does have a red stop button. The red stop button is a PDL model 51 with a key, or whatever it may be. Then we progress to the OQ. The OQ is the operational qualification, and this checks the functions. It says when I push the stop button, the machine does actually stop and various safety interlocks react. Assuming it passes that, we then go to PQ, which some people say is performance and some people call it production. It basically tests that the machine does what it's supposed to do to the extent that it's supposed to do it. So we can say that the IQ is a test to check that it's designed right. The OQ is a test to check it functions correctly, and the PQ checks that it does actually do what we want it to do. So this is our V model, and you can apply this to any project. So you can basically say you identify your need, you form a committee to decide what you require, you design something that behaves the way that will fulfill that need. You then turn the design into wiring schematics, engineering drawings, calculations about mechanical forces and so on. Build the thing, and then you test each step. And at any stage in the process, anything happens. So for example, I do the IQ OQ and it turns out that either my build doesn't match my design, or we've made a mistake and actually we've missed something in the design. It feeds back to the URS. If at any stage during the project or after the project's completed my need changes, it feeds back to the URS. Everything goes back. The URS is a living document that constantly is adapted to suit whatever the latest version of our project is. Now, if you are only designing something, then you're only interested in this half of the process. You're only interested in specifying, designing, and coming up with a specific design. But you need to be aware that somebody somewhere will be interested in this half of the design. And so everything is about being smart. It's about quantifiable